Okay, students, so we're realizing here with this curve sketching that a lot of information comes from the first and second derivatives. So I'm going to be going over the process here of finding the first and second derivative for this last function. I do also want to point out that we, from our notes, hopefully you had gone through all of those examples, both in the video I posted online for the notes. If you hadn't yet, really, I hope you have. You take a look at that. I just will mention real quick before I get into that, the horizontal asymptotes on this come from examining the limits as x approaches infinity and as x approaches negative infinity, okay? So you need to consider that when finding the horizontal asymptotes, okay? So let's dive into finding the first and second derivative for this function, okay? We're going to be using quotient rule. I'm going to rewrite this first as 3x over x squared plus 4 to the 1/2. So to get the first derivative of f of x, we're going to take the derivative of the top, which is 3 times the bottom, x squared plus 4 to the 1/2. We're going to take the derivative of the bottom. It's going to involve chain rules. So we're going to start with the power rule, 1/2 times x squared plus 4 to the negative 1/2 times the derivative of the inside 2x times the top 3x all over the bottom, which is x squared plus 4 to the 1/2 squared. If you consider that, the bottom would be x squared plus 4 to the 1/2 all squared. Really, it just means take the 1/2 and the 2 and multiply them together, and you just get 1. So really, this part there is not needed. The bottom can just stay x squared plus 4. Now, when you go through the simplifying process, I want to point out, you'll see here this negative 1/2. So really, my thinking when I see this is I'm looking at this term, all this here, I'm trying to figure out really what's going to be on the top of that specific term and what's going to be on the bottom. It's a lot of multiplying, and it's a lot of multiplying there. So when I go through that process, really that's my goal, is considering like what's going to be on the top and what's going to be on the bottom. And this is all over, again, x squared plus 4. This first part, since I know there's going to be a denominator in that second one, I'm going to go ahead and write this as 3 times x squared plus 4 all to the 1/2 over 1. And on the right side here, I'm trying to consider, again, what's going to be in the numerator and denominator of that specific part of the top there, of all this stuff right here, okay? And so on that right side, I know there's going to be a negative 1, or there's going to be, well, I guess I should just say 1. There's going to be that 2x and that 3x. So really, that all ends up as 6x squared here on the top. Okay, and then in the bottom, that's where this 2 and all this ends up. Okay, so that would end up as 2 times x squared plus 1/4 to the x squared plus 4 to the 1/2. All right, so now I got to combine everything. Now, again, I notice here that this is like a 6 and then this is a 2. I could go ahead and reduce that if I wanted to. I don't feel like rewriting it, so, you can erase that, I guess, and simplify that, if you wanted to. I'm just going to leave it there for now and wait until the very end. But I could see you just taking that 6 and 2 there and dividing it out. But I'm not going to do that just yet. So what I am going to do is, I'm just going to go ahead and get rid of this for now to make the writing here a little more straightforward. I'm going to take, and really, I've shared before that I'm really just going to take the numerator here and multiply it by x squared 2 times x plus 1/4 to the 1/2, because I'm really multiplying the top and bottom by it, so I guess I can go ahead and write it out. A lot of times I ignore that numerator and just go ahead and really just write it out the one time, because I know I'm multiplying the top and bottom by it. And that gets you 3 times 2 there is 6. And then the x squared plus 4, you really take the exponents and add them together, and you get really just 6 times x squared minus 4. Then I'm going to subtract that 6x squared from over here. So that really takes care of all of that there and all of that. Okay. And then that is all over 2 times x squared plus 4 to the 1/2. All over x squared plus 4. Now, I'm going to really combine 2 steps into one here. And at this point, what I'm going to do is distribute all the way up. I'm going to distribute this out, okay? And I'm going to get 6x squared plus 24 minus 6x squared. So you'll see those will cancel. All over 2 times x squared plus 4 to the 1/2. Now what I'm going to do is I'm going to take this part here and really imagine that as divided by 1. So I'm going to go ahead and just multiply by the reciprocal. And now I have it down to really just like, one fraction, okay? And so from there, these cancel, and you are left with 24 times 1 on top, which is just 24, all over, and I guess we can just put that in parentheses. This would be 2 times, what you're going to do is really take the 1/2 and add 1. You're going to add the exponents to get a total of x squared plus 4 to the 3/2 power. And then you can divide there by 2. So if you had gone ahead up here and divided out, so if you had gone back up here and divided out like that 2 there, I'm guessing this would already say 12. And so that part really, that 2 eventually does divide out. And we end up with a first derivative of 12 divided by x squared plus 4 to the 3/2. Seems like a lot of stuff to get to something that doesn't seem maybe all that complicated, okay? Now from here, a couple observations. Notice that the first derivative is never going to be 0. We know that, again, from our discussion on this is always positive. So there's really no critical numbers. And it's no surprise that this graph doesn't have any max or mins. And in fact, what you'll also notice is that, and an important note I want to make, is that since there are really no critical numbers here, I could pick any x value, plug it into this first derivative, and it will tell me whether the function is always increasing or always decreasing. That is an important note to make there, okay? All right, so now let's look at the second derivative, okay? Second derivative. So we're going to take the derivative of the top. So again, we're going to do quotient rule. Derivative of top would be 0 minus the derivative of the bottom, which would be 3/2 times x squared plus 4. If you subtract 1 there, you get 1/2 times the inside, which is derivative inside, which is 2x, times the top, which is 12, all over x squared plus 4. And that would be 3/2 times 2, which would just be 3. And again, that part there is coming from, if you're unsure, that part there coming from taking the bottom x squared plus 4 to the 3/2 and squaring that whole thing. It's really just taking 3/2 times 2. Now, important observation. I want to make, okay? I've discussed this, I know, with some of you, and I'm hoping maybe more and more catch on here, okay? Is, we are going to simplify that second derivative to really solidify a lot of things here. But I want to talk about this for a second, okay? When we explore the second derivative, we're trying to figure out where is it undefined, does not exist, or zero, okay? We know from the function, the first derivative, second derivative again, that this denominator is never zero. There's no issues there, nothing we need to worry about. If you look at the numerator, really, you can think of this almost like looking at it like it's in factored form. You can really just ignore that zero there. Let's just drop that zero, okay? And look at this in terms of really all the different components. You got this negative 3 halves. We don't have to set that equal to 0. That 12, we don't have to set that equal to 0. This part right here, this x squared plus 4, that's always positive. Don't have to worry about that. Really, this part right there is really the only component that we're worried about causing any potential concerns. So I could really see you analyzing this and saying, let's just set 2x equal to 0, which is what we're going to end up doing in, we're going to notice when we get to the end here, it's not going to be 2x we're going to set equal to 0. It's going to be something a little different, but it's going to be perhaps maybe no surprise to us. Now, again, I don't want to sit here and say I really want us all approaching this from the standpoint of, well, let's just set that 2x equal to 0 and we're done. I think that's a slippery slope. I think we're going to try to maybe apply that too often and maybe get ourselves into some trouble. I'm just trying to hopefully understand that, really start to make connections between what we end up discovering and what we already see, okay, and not be surprised by things. So, with that being said, okay, I'm going to continue simplifying this second derivative. Now, a key here in simplifying this second derivative is, we could actually go ahead and we could do this. We could go ahead and just take that negative 3 halves, that 2x, and that 12, multiply all that together, and you get negative 36x times x squared plus 4 to the 1/2 all over x squared plus 4 cubed. Okay? And so from there, recognizing that, we really can simplify this a little more. Like you can take, you can use your exponent rules here and look at this and say, well, you got x squared plus 4, you got x squared plus 4. So you can subtract the exponents and simplify that a little more and say, well, the second derivative of x would be negative 36x divided by x squared plus 4 to the 5/2 power. So you have your second derivative. And again, you would say, well, I really just need to set that negative 36x equal to 0. You'll find your possible points of inflection to really only be 0. And when you explore the second derivative, you'll realize to the left it is concave up, the right it is concave down. It should be then hopefully no surprise that when we get to this graph, what you'll end up seeing, you add in all the other details and you'll see, just ignore that floating equal sign there. You'll see that, there's like a point of inflection here and it's going to do something like this, and you'll see those asymptotes at 3 and negative 3 when you look at those limits that I had discussed. So, again, hope this helps and provides some more detail. Let me know if you have any questions.